Originally from North Yorkshire, Jamie graduated from the University of Manchester in 2013 with a first-class master's in theoretical physics. During his PhD research at the University of Leicester, Jamie investigated the potential for new graphene-based photodetectors, from X-ray to terahertz. Jamie submitted his thesis in March of 2017 and was awarded his PhD in November of 2017. Alongside ongoing work on graphene, Jamie is now also involved in researching new technologies for and applications of the camera for the Cherenkov telescope array. Please welcome Dr. Jamie Williams.
Hello everyone, my name's Jamie Williams and I'm from the Space Research Centre at the University of Leicester in the United Kingdom. Today I'm going to talk about how I'm using software-defined radio for education through my radio educational outreach tool that I've developed and I'm the principal investigator for. This project was funded by the Science and Technology Facilities Council and the Institute of Physics, and I'd like to put on record my thanks to them from the start. To start with, I'll outline the need for new educational resources, in particular in the United Kingdom, and then I'll go on to introduce the radio concept itself and how we're using commercial off-the-shelf electronics and software-defined radio. I'll discuss our bespoke Python-based software that we've developed and the 3D printed case that we've designed. I'll talk through our initial deployment to our free partner institutions across the UK and then discuss some of the potential future developments of the technology. The need for new educational technology stems from the need for new and updated teaching resources and activities in the classroom. Teachers and students regularly comment at how outdated science experiments in particular are, and new technology will allow them to undertake new experiments in the classroom. It will also allow that teaching to take place outside of the classroom, in particular at home during the ongoing pandemic. Educational technology is also linked to improved educational attainment. In particular, in a recent study in the UK, there was a correlation between science GCSE attainment and ICT usage. New educational technology is also needed to address skills shortages, in particular digital skills shortages, given that approximately 90% of jobs in the UK are predicted to require digital skills within 20 years, and science, technology, engineering and mathematics skills shortages given the changing needs of the economy. To address these challenges, I'm leading the development of the Radio Educational Outreach Tool, otherwise known as RadEOT. RadEOT is a multi-purpose, handheld, portable educational technology that has been co-designed with teachers and practitioners from across the UK. The user collects freely available radio data using a software-defined radio dongle built into RadEOT. This data is visualized via a Raspberry Pi and a touchscreen, and then the data that has been acquired is utilized in questions that are linked to physics, mathematics, computer science tasks via a bespoke Python-based graphic user interface that we've developed. The user can continually collect data, visualize the data, and answer questions on that data to support their education. To build RadEOT, we've used commercial off-the-shelf electronics. This has enabled us to reduce the cost and improve the reliability of the technology versus other approaches. This has also enabled us to make this as widely available as possible. Anyone can purchase the technology and then build a radio unit from that. We're using a software-defined radio USB dongle, the DVB-T820T2 and SDR USB dongle that was purchased for £10. We're also using a Raspberry Pi, and that's a Raspberry Pi 3 or up, along with a 16GB SD card. We're also using a 7-inch touchscreen, which is directly compatible with the Raspberry Pi, and we're also using a 20,000 mAh battery pack to make it portable and usable both in the classroom and outside. The 20,000 mAh battery pack gives us approximately a 4-hour lifetime for RadEOT. So what can RadEOT do? RadEOT currently has 4 applications that are built into its Python-based graphic user interface. All of these applications have been co-designed with teachers and practitioners to align with classroom teaching in physics, mathematics and computer science, among others. Activities are tailored to the age of the individual user, and this is controlled via a drop-down box when the user begins the task that they are doing. The Python-based graphic user interface is easy to amend to and add to, and it can be downloaded for free from the GitHub account that you can see here. So anyone can download the software, anyone can amend it, anyone can build a new task to align with the teaching outcomes that they need. So to begin with, I'll talk about the FM radio application, which allows the user to listen to local and national radio stations via the RTL_FM component of the RTL-SDR package. It allows the user to control the frequency of the radio station they are listening to between 88 and 108 MHz, to control the gain, and to control the sampling rate. And all of this will allow the user to learn about the relationship between frequency, wavelength, speed of light, and photon energy of the radio signals that they are listening to. So to start with, in the top picture, you can see that this person is listening to a preset radio station at radio 1 for 10 seconds, and they can control the stopping and the starting of the radio that they're listening to. They're able to listen to a particular frequency as well. In this case, they're selecting 98 MHz with a gain of 25 and a sample rate of 44.1 kHz. This data then can be used for the questions. In this case, the question is linked to the range of radio stations, but you might also expect a question linked to what is the energy of a photon at 98 MHz. Complementary to the FM radio application is the radio database application. Similar to the FM radio application, it allows the user to visualize the entire radio background rather than between 88 and 108 MHz. So this allows someone to visualize anything at 20 MHz or anywhere up to approximately 2000 MHz. The user can control the frequency between any of these values and use an Office of Communications database to understand what the likely source of the radio background is that they're observing. They can use GQRX software, which is loaded onto the Raspberry Pi, to visualize the waterfall and the Fourier spectrum, and they can continually go back, change the frequency, and go and look at the waterfall, the Fourier spectrum again. The frequency that they're using, again, is linked to the questions that they can answer, and this can be a repeating cycle. The next application is the hydrogen line, where we use the software-defined radio antenna to detect the hydrogen line signature at 1420 MHz to identify the center of the galaxy. Instead of using the standard antenna that comes with the commercially available software-defined radio dongle, we can design and build our own horn antenna to optimize the response that we get from the hydrogen line at 1420 MHz. To enable this, we've built a calculator which is included in the RadEOT software, which will allow you to vary the frequency and the gain of a particular antenna, and this will return the dimensions that are required to obtain the response that you require. This is something that we did in Leicester. You can see here that a horn antenna on a pivoting structure that I built with my project student, and we were able to use this to pinpoint the galactic center. So the results you see in the bottom left are results from one of my project students who, by pitching the horn antenna, was able to identify the strongest response, which correlated with the galactic center. So the responses can be used to answer some of the questions that we have, and these are linked a bit more towards the astrophysics as well. So in this case, we are asking a question about how the 1420 MHz signal would be redshifted, in this case, by a factor linked to the redshift Z. The final application in RadEOT is the flight tracker. This picks up aircraft transponder signals within approximately a 40-mile radius, and we've tested this both around Leicester and around my house in the northwest of England. I live southwest of Manchester city centre, and I can detect signals as far afield as Blackburn, which is about 40 miles away, and south of Manchester Airport, southeast of Wilmslow, Knutsford, as you can see on this map. These signals have height, speed, bearings, identifications, etc., all within the signal that we're detecting. And this can be used to make physics and mathematics lessons covering dynamics and mechanics more exciting and more responsive to what the students are seeing. So instead of a car travelling down a road at 20 miles an hour, how far does it cover in a minute? The students are able to actually get the questions themselves. They're able to say, that plane that you are seeing right now, travelling at 500 miles an hour, how far does it travel in an hour? So for instance, the data that we're able to collect, you can see here for a KLM plane that I observed earlier in the year, had a heading of 50.68 degrees. It had a rotation of 4.61 degrees. It had an altitude of 8,175 feet. And we could also identify that it was a KLM plane. So that can all be used for a question. So the question that you can see here takes the speed, 527 kilometers per hour. How far will the plane travel in 5 hours? And I get it correct. So that can be used for any of the parameters that we see. We designed a 3D printed case that could encapsulate all the different components to form one robust shell for RadEOT. The case itself is formed of two components. The components are bolted inside, the two are bolted together, but you're still able to remove all of the individual components if required. The shell is 3D printed with PLA tough, and this took approximately 1 day to form one individual unit. The design itself is available to download from the GitHub page that you see here, and this can be edited, improved upon, and amended as required to fit the technical components of any individual user. We were funded to manufacture 27 RadEOT units and to deploy these to 3 partner institutions in different parts of the country. The deployment began in February 2020 with the deployment to our partners at a school in the northwest of England and to a charity in Yorkshire. With the school, we had 95% positive engagement with the students in the initial deployment, and I'll be returning there in the next few weeks to provide the final updates to the software. When I presented at our partners in North Yorkshire at the charity, I was fortunate enough to meet the now Chancellor of the Exchequer, Rishi Sunak, who described it very positively in a local newspaper publication, describing it as a game-like piece of equipment and could clearly see the benefits that it would have for science, technology, engineering, and mathematics lessons. We're due to deploy shortly to our third partner institution in Leicester, with the rollout complete by the end of December 2020. So in summary, RadEOT is a multi-purpose handheld educational tool that utilises freely available radio data to support educational activities both inside and outside the classroom. The software that we've developed is completely open source, so anyone can develop it. The components that we utilise are all freely available, so anyone can build it. There are a wide range of possible developments that could include utilising signals from the International Space Station, downloading data from NOAA weather satellites and tracking satellites across the sky. Depending on the software-defined radio, there's potential for Wi-Fi and 5G tracking. And also there's the possibility of including other technologies, to include perhaps an ultrasound transducer for biology lessons, or potentially to include voice activation to widen the use of RadEOT as far as possible. I'd like to acknowledge the role of our funders, the Science and Technology Facilities Council and the Institute of Physics in helping us develop this technology, and I'd like to thank my team, Felicity Easton and Jordan Penny, John Lappington, our head of group, and our project students Emily, Ellen, Dan, Natasha and Drew in helping to make this technology a reality. I'd also like to thank our partner institutions, the Skill Mill, Formby High School and the National Space Academy for their involvement in the project and helping it to get it to where it is today. Thank you for listening. If you have any questions, please do let me know.